Good morning, ladies and gentlemen. It is indeed an honor and pleasure for me to introduce Professor Hoffman this morning to you.
So what are protochemistries? Protochemistries are chemistries, that transformations of matter that were done before there were any of you around. So meaning before there were professional chemists. And I want to tell you about these things. Now, I am not going to tell you why I'm telling you these things. That will become apparent, I think, in the course of the story, but I will tell you a little bit at the end. And I said story. So storytelling is also an innate human activity. And like many things that are not mathematicizable, it has been downgraded in science. But it is in fact a basic human activity. And I'm going to tell you some stories of the often anonymous makers of the objects that you'll see. But also there will be detective stories of the people in contemporary times, chemists who have made these things. So let me begin. This is a story, and this is one of the detectives. This is Heather Lechtman, who is a metallurgist with historical interests at MIT, long at MIT. And this is a story of a culture we should know more about, which is been given the name pre-Columbian, which is horrible. But the right word might be Andean cultures of South America. The one we know because of the Colombian and the Spanish invasion of this region afterwards, the one we know well are the Inca. The Inca had a short run on the world of about 100 years. And preceding the Inca, and during that run, they in fact governed an area that ranges from Colombia down the west coast of South America, all the way halfway down the long leg of Chile, and a region of about 4,000 kilometers that was administered very well in various ways. But preceding the Inca were a series of cultures whose names you see here overlapping, Moche, Wari, Chimu, which range from about 300 BC to the time of the Inca. And then the end of the Inca period, 1533, is the Colombian, is the Spanish invasion. The marks of this culture are very interesting. There was no writing as such, though there was a counting system of various kinds. And the technology, the arts are quite impressive, and they were expressed mainly in three areas. One of them is ceramics. So you see here some typical ceramics from this period. And just about every element of contemporary art in the West is expressed in these ceramics. They are figurative, they are expressive. Look at the expression, for instance, in that little modest sculpture over here. They are abstract as well, and with all full command of the elements of abstraction, and they are funny. And they were intended to be funny sometimes, as you can see in some of these. The other thing which is absolutely incredible and much better preserved than any other part of the world for reasons of climate, a very dry climate, is the textile art. So here are two examples. You can see the rather abstract one at left, and you see the butterflies in the design at right. These are from about 500 AD or so, both of those. Very well preserved. Incredible control, as you can imagine, of the dyes, but also of the design elements and the art of weaving. And the third thing that they were good at was metalwork. but very interesting metalwork, because it did not concentrate on the metals that were the elements of civilization in the Middle East and in China, which were, they had no bronze, they had no steel, nothing of any military value, but they worked in silver, copper, and gold. And the metallurgy was quite incredible. Here are some of the objects from a museum in Peru that you see. And and Heather Lechtman has investigated something about the gold objects, and I want to tell you something about them. Here's, for instance, one thing she found. A rather unprepossessing idol, just a few centimeters high at left, but when it's examined, the back of it is copper and the front of it is gold. And the gold, when examined in a cross-section, is in a layer about 2 microns thick, looking for all the world, as you see in a cross-section, as if it had been electroplated onto this, except that there were no batteries to do this. Now, part of the story is simple, and it's something we demonstrate to students in an introductory course. You take a copper coin, and if you were to dip it into a gold solution, the gold would plate out in a thin layer on top of the copper, but would not persist, because it would flake off. Firstly, it wouldn't form a thick layer. It would form a layer just as thick as this, but it would not persist. But she showed that the temperatures available in their metallurgical techniques were such that they could anneal the copper layer that was on top of the gold layer that was on top of the copper, and it would remain affixed and not flake off, as you would happen with that penny that we do in a laboratory. Oops, now I have pushed the wrong button. Now, one thing about gold, of course, here is a burial. This is next to the tomb of Tutankhamen, opened up not too long ago, and you see that everything corrodes to a various extent. And incidentally, about textiles, we have very few antique textiles from Egypt, for instance. The earliest ones we have are from the Fayum burials, which are from around the time about 2,000 years ago. But what you see there, what I want you to see, is the gold vessel there. That gold vessel, and that is as true of Tutankhamun's tomb as it is of this subsidiary burial, that gold vessel, when it's opened up, shines as brightly as it did on the day it was buried. And the reason has to do with, of course, what else? The electrochemical series. And as you notice that on this, gold is fairly high up. This is in terms of oxidation potentials right now. Anything in the world reduces gold ions to metallic gold. And so metallic gold does not tarnish and remains where it is, and that is that is not the problem in making this. The problem in electroplating the gold on top of the copper in that burial is getting the gold into solution, because anything gets it out of solution. Anything gets gold out of solution. So they had the gold there, gotten in the classical ways, and the European development of chemistry found in the hands of the alchemists, actually, a way to dissolve gold in what you know as aqua regia, which is a mixture of hydrochloric and nitric acids. So, and the actual gold goes into solution as the soluble gold tetrachloride anion. Once you have it in there, it comes out, as I said, with almost anything, whereas you deacidify the solution. But you need both the hydrochloric and nitric acids, but the Andean civilizations did not have hydrochloric and nitric acid, but they did something better. They essentially, and this is Heather Lechtman's work, recreated the ionic atmosphere of a mixture of hydrochloric and nitric acid using local chemicals available to them. And this, I just show this, friend Martin Polyakov. This is apropos scientific education. Sometimes chemistry education comes out of left field. No one in the world could have predicted the popularity of the periodic table videos that Martin Polyakov and some friends made. These are the most accessible videos that there are. The reason I show it here is that one of them shows gold dissolving in aqua regia, if you want to see this, because it's an expensive demonstration to do otherwise for you, but you can show this very well. He has one. What she reconstructed it from, they got the chloride from salt, that's around the world, the nitrate from Chile saltpeter, which is potassium or sodium nitrate, which is mined in abundance. The thing that was missing, the hardest thing, was making the solution of the Chile saltpeter and the normal salt acidic enough to create the atmosphere of hydronium ions now. And that was accomplished because she showed that in they had some other uses of alum. The men here, and the women too, of a certain age will remember something called a styptic pencil. A styptic pencil is what you use when you cut yourself shaving. Okay, that's alum. And alum is very acid, and the reason the styptic pencil hurts is because it's so acidic. So this mixture creates essentially the sodium ions and the aluminum ions go along for the ride in the solution and creates an ionic atmosphere. This is her recreation at Wright of the process using those local chemicals. Interesting story about batteries. There is a persistent but still not proven analysis of a find near Baghdad of what looks for all the world like a battery. It dated to about 200 AD, and it's a ceramic jar. There's a recreation at Wright with an iron bar now, and the iron, and there is copper also around, and there is an asphalt stopper to this. And you need a solution in there. Grape juice fermenting will do, and this creates actually a low voltage across. But there is very little, there's just one find. People are still debating this. Just to give you an idea, again, back to the Andean culture. Here is a mummy mask that they have. This is 74 centimeters across, about half of the size that you see here. You can see why the Spaniards thought they had found El Dorado, because when you have objects which are as large as this, made out of gold, the metallurgy is very interesting because it was made from an alloy of gold, silver, and copper called tumbaga, which has been rediscovered independently around the world. 48% silver, light on the copper. That alloy was repeatedly hammered to bring the copper out, and the copper was dissolved with a very acidic pickle that they made from some plants. And then with another, the silver gold remaining, the surface layer was removed with another plant product, a corrosive paste made from some plants, including some alum in it as well. The method is called depletion gilding, and this is what was used to make this mask. Still in South America, totally different. Also in Africa, there is a tuber-like crop called cassava or manioc. If you ever go to Brazil, you will be served as a typical staple food crop, something called farofa, a wonderful tasting cereal, and that is made from manioc and cassava. It comes in sweet and other bitter varieties. The bitter variety has some cyanogenic glucosides in it. If you eat it, you will not be very healthy directly. But the glucosides are very labile, and these decompose simply in boiling water. So the manioc or tapioca has to be boiled up, ground up and boiled up and then dried, and all the water extracted. And this is a extraction device that's where you twist it and it squeezes out all the water. It's made from straw. This here used in the Amazon. But this has been in difficult times. This is a food crop for not just a few people, but something of the order of 500 million people around the world in tropical regions. There is a picture of the tuber. Some simple chemistry that someone found, no archaeology here needed, found as a result of experimentation. Here, now coming back to our part of the world, at the top are 3 masterpieces of ancient art. At left, a wall painting from Luxor, or Thebes. In the center, the Gate of Ishtar, which once stood in Babylon, and as a result of some imperialism, for a change not American, but German, found its way to Berlin, where you can see it now. And at right, you see a Hellenistic wall painting, roughly of the Fayum period, a period of, as you can see, realistic representation which preceded the Italian Renaissance by a mere 1,500 years. The green or the blue in these is not the natural product which you see at lower left, which was available to the artists throughout history, which is powdered lapis lazuli or ultramarine. The chromophore in lapis lazuli is very interesting. What gives it the color. That was also always available if you were rich enough. Giotto's patrons in the Scrovegni Chapel in Padua used this, were rich enough to use this. It gives a beautiful color, but the blue and the green that comes from the blue in all of these 3 masterpieces of ancient art is not lapis lazuli. It is an article of commerce in the ancient world, which is a byproduct of the Egyptian mastery of making glass and enamel. It's essentially a glass frit with silica, natron, and the chromophore is a ground-up copper salt in these. This is Egyptian blue. It was sold throughout the world. It's a calcium copper silicate. In another part of the world, some of you may have seen, if you've been in China, the famous terracotta army from about 200 AD. They don't look like this, but note the blue hue. When they're excavated, they look more like this before they are reconstructed, but you can see the traces of the color. They were all multicolored, and the blue in these is closely related to the Egyptian blue. And there is an open question about whether trade routes were open. There were between China and Egypt along the Silk Route, but this is made in a slightly different way. And a former postdoc of mine, Heinz Berke, who's a professor just retired at the University of Zurich, has reconstructed the making of this. It's essentially also a silicate with a copper mineral mixed in, but this one is based on barium, whereas the other one, the Egyptian blue, is based on calcium. There is a very unusual step in here, which was part of the reconstruction. The barium comes from barite, from barium sulfate. But as you heat up barium sulfate, it's easy to release at the temperatures available. We know that because we know what the temperature that is needed to make porcelain, which is a relatively high temperature. The temperatures available to the Chinese metallurgists, there is an important admixture of a lead oxide, I'll come back to lead later on, which takes up the SO2, SO3 that's emitted, and that allows the freeing of the barium oxide, which is important, and that is Heinz Berke's discovery in this. the overall chemical reaction has no lead in it, but you need the lead as part of the process. And that was the interesting chemistry that was discovered. Oh, there's a chemical structure. It's a square planar copper-2 complex, but let's not worry about this. Back to our part of the world. These are the shades that you can get from Tyrian purple. A pigment that was of value to the Romans and in the Middle East in general. A shade, a range of shades going from a blue, the dyer's art can make that blue as deep as you want, to a reddish purple, which is a characteristic color which is not accessible from all sources of the element. The art was known to the Phoenicians, so we are in the right place in Malta, having been founded by the Phoenicians. The art of making the Tyrian purple was mastered by the Phoenicians, and this is some testimony to the economic importance of that. What do people put on their coins? People put on the coins on one side the ruler or pseudo-ruler like the Queen Elizabeth. On the other side of the coin they put some sort of thing emblematic, often of importance spiritually to the country. And in this case, what is down here is the foundation myth of the city of Tyre, or Sur. And this is the story that Hercules' dog, this is a Hellenistic influence here, Hercules' dog was wandering along the beach, found a shell. You see the shell. You'll see in a moment how well it is depicted anatomically. And bit on a shell, and its mouth was colored purple. And that was the origin, supposedly, the mythic origin of the purple industry. Meanwhile, a little bit to the south and west, the Hebrews wrote this into the Bible. So this is in the middle of one of the less interesting parts of Numbers, Dorim. There is a passage, the Lord said to Moses as follows: "Speak to the Israelite people and instruct them to make for themselves fringes on the corners of their garments throughout the ages. Let them attach a cord of blue to the fringe at each corner. That shall be your fringe. Look at it, and you recall all the commandments of the Lord and observe them, so that you do not follow your heart and eyes in your lustful urge. Thus you shall be reminded to observe all my commandments and be holy to your God." This is actually repeated twice a day by observant Jews. It's a very important passage. It's followed by another interesting passage of Korach, which is actually one of the passages of the Torah that's repeated in the Quran in a somewhat different version. But you see the blue here. The word for blue is not the modern Hebrew word for blue, nor any of the other two words for blue that are used in the Old Testament, in the Torah, Karailan and Argamon, but it's a word techelet, which is used here. It's used about 50 times in the Old Testament, and to describe also the prescription for the priests for the garment of the high priest in the temple, and also for some hangings and in the temple. And the blue is then discussed in the Talmud, the work of 50 volumes or so. I used to be able to say a Talmud is about encyclopedia size, but young people in the audience have no idea what an encyclopedia looks like. They think Wikipedia, so I can't say it anymore. The Talmud has prescriptions on how to live your life. It's hard to live your life on the basis of these 5 books in detail. And so it does that in some detail and offers and makes it clear that the blue here that is used here, that the chelet, comes from snails in the Mediterranean. And here, the fringes are in a ritual garment that religious Jews, relatively few in this room are religious, wear under their clothing, a four-cornered garment. And there are also as an echo of this in a prayer shawl, and it has these fringes, and here is one of the fringes should be in blue. The Israelites lost the ability to get this blue around 600 AD. The Romans lost the ability to make the Tyrian purple. They had made it an object of great rarity and restricted use, using the Phoenicians to manufacture it. But they lost that too around the time of the fall of Constantinople. And so since that time, if you go to an area where there are religious Jewish kids who are running around with these fringes hanging out of their clothing, you will see that the fringes are all white. And there isn't a blue fringe in it. I'll come back to that in just a moment, but I'm again pressing the wrong button. Here are the snails that they come from. 3 species of snails that are in the Mediterranean. 2 in the Murex family, 1 hemistoma. There is a hypobrachial gland in here. It's been dyed, about 1 centimeter long, about 1 millimeter wide. You break open the snail. You have to kill the snail to do that. And if you take out that gland, if you excise it with a sharp knife, before your eyes, if there is light around in a photochemical enzyme catalyzed reaction, it turns pus green, and then blue before your eyes, and it'll stain your hands for about a day or so. After that, you can wash it out. These snails are a veritable chemical factory for killing things. They are carnivorous and cannibalistic. They eat other snails. Another snail comes up, closes its operculum, crawls inside its shell. What the murex will do is take out a proboscis it has, use a gland in which it produces some sulfuric acid, take some sulfuric acid, dab it on a calcium carbonate of the shell, soften it up, use the proboscis to drill a hole through the shell. When it reaches the flesh of the other snail, it injects a neurotoxin, or actually a relaxant, which makes the other snail open up its shell, and then it eats it up. So much for the romance of the natural world. I learned these things. This is not obviously which someone who is a quantum mechanic does, but my friend and Ehud Spanier, who is a professor of marine biology at University of Haifa, was the one who introduced me to that story. You can see from that little sculpture on the coin, this is about 1.5 millimeters big. That's not a bad small sculpture of the murex snail. That's almost 2,000 years old, the sculpture. These snails are found around the Mediterranean. Here are some of the archaeological sites where it was found. There are shell dumps. This was a major industry. It takes 10,000 snails to produce enough pigment to dye 1 Roman toga full blue. So there are many snails were killed in the process. I have myself stood in Tel Dor and in the island of Djerba in Tunisia in snail dumps dating back to Phoenician times. The Phoenicians, of course, made major settlements there as well as in Malta. There's a wonderful book by Dominique Cardon, who heads up a CNRS research group at Lyon about natural dyes, and tells the story in some detail. They are found also around the world, different species which produce the purple. And those beautiful fabrics that I showed you, those are also dyed, the blue in them, with a snail purple. Some of them a mixture of snail and a purple from another source. But they are found in the Sea of Japan, near Borneo. They are found around the coast of South America. And in each case, the cultures found a way to use this blue from the snails. But perhaps it was best developed in the Mediterranean. All along, there was another source of the blue. In the area that's in dark blue here, in tropical regions, it is a plant in the pea family, Indigofera. This gives away the name of the pigment, which is indigo. In regions which are more temperate, which is the light blue, which extends all along Europe, even into southern Scandinavia, but certainly into the UK, there is another plant, totally different family, Isatis tinctoria, which is called in English woad, in German Weid, in French pastel, which was used widely to create, to use that same blue, at least on the blue side of the range. And so now there is a difference. This is, of course, a folio from the incredible blue Quran that was composed, or written down, rather, in Fatimid, Tunisia, probably in Kairouan, in around the 9th century. Gold painted on indigo-dyed sheets of parchment, not paper. That has probably been dyed with the plant indigo, not with the snail indigo. Though the tests are, as far as I have not found the tests on it. The range of that one got was on the blue side. So, all along there are all these ways. There are actually several ways. Oh, incidentally, when I give this story to people who are non-scientists, people ask me, naturally, what the heck are 7 families of snails and 2 families of plants widely differentiated from each other, making the same pigment? And I said, by asking that question, you are well underway to being a scientist. So the story is that the precursor of indigo, I'll show you the molecule in just a moment, is a part of biochemical evolution that was settled on early. It's on the way to tryptophan, I think. And there is the precursor of indigo in every organism from E. coli on. I could make an indigo out of you, except you don't have enough of it. So now comes the other question. Why do these families of plants overexpress the precursor of indigo? This is the kind of question which my late colleague Thomas Eisner, a wonderful neurobiologist, insect biologist, together with Jerry Meinwald, would ask. And the question is still unsolved as to why what value is it to the organism to produce so much of the precursor of indigo? But it's there and everything. Eventually, cultural evolution catches up with a vengeance, as I'll tell you in a moment, to biological evolution. And cultural evolution is what chemistry is, one aspect of cultural evolution. So you know the story of the dyestuffs industry. Synthetic dyestuffs originated in the UK by Henry Perkin, and then the Germans run with it. And by 1872, these are some samples from the Deutsches Museum, we have the aniline dyes. At left is a facsimile of a letter by Adolf von Bayer to Heinrich Caro, the head of BASF, a company that exists to this day. And he's telling him he's gotten the structure of indigo. Within 2 years, BASF is making indigo. Within 1 year after the commercialization of aniline dyes, they are found in remote villages in Iran. That's how quickly good technology spreads. And this is in the 19th century, before Amazon. That technology spread widely. The first synthetic black ruined the wool with which it was dyed, and that led to an imperial edict in Iran, in Persia, that forbade the use of the aniline dyes. This is indigo, or rather this is dibromo indigo. If you have hydrogen instead of bromines, that is the indigo. The indigo itself is on this shade. The plant indigo can never give the reddish shade by itself. The reddish shade is the dibromo compound, and the bromine is in the sea. That comes from the sea. The snails that produce this with a dependence on the climate and on gender. And just to make things more interesting, they change gender every 3 months. So that there's a varied production of the red. The natural red can only be gotten from the snails, but the bluish side of the range can be gotten from the other things. This is very interesting from a point of view of sociologists. These are the labels from BASF when it first sold the indigo in 1890 to 1900. This is a story connected to the German in Saxony in first decade of the 18th century. Europeans finally learn how to duplicate Chinese porcelain. What patterns do they put on a porcelain in order to sell it in Europe? Do they put European patterns? Of course not. They put Chinese and Japanese patterns. So to sell something which was initially associated with something coming from the tropics, you put exotic labels on it, of course, if you want to sell it. And this is another part of this story. This I got from Klaus Dietrich, a historian at BASF. Eventually, the synthetic indigo takes over. Within 20 years, the Indian dye-stuff industry, the plant indigo, is ruined. And since that time, everything is a synthetic indigo. There is nowhere in the world a commercial industry based on the plant indigo. On snails, it's uneconomical, would never be done. Though there are interesting revivals for quasi-religious reasons in Israel. But in terms of plant indigo, the only place is in Japan, and I'm wearing a tie, which is a product of that indigo industry. So the thing to admire about Japan is not that they can make CDs and cars better than we can. They can. But that they can do so while preserving their national culture. That's the real success of Japan. And so the way to see this is, if you go to Japan, go visit that archetype of Japanese culture, which is a department store. They are very typical. They're little girls at the entrance greeting you in a ritual way. And then you go in, and it's full of everything you wanted in the world, but there is one floor in that department store, usually the 6th or 7th floor, which will have the products such as kimonos. And there's enough of a premium attached to buying a kimono for a wedding that has been dyed with plant indigo rather than synthetic indigo, and enough of a homogeneity of culture that you can enforce this, that it is still a going industrial concern. I told you that the plant indigo, the snail indigo, when I break open that snail and take out that gland, it turns blue and stains my hand. But it's like, for the Americans in the audience, if you've ever handled black walnuts from a tree, they make your hands black. But in a day or two, it washes off. The same here. Nothing has changed. You cannot sell an article of commerce that washes off in 2 washings, okay, completely. And so there had to be a way to make a better dye of it. And that was done in ancient times. Here is a prescription. It's called the Stockholm Papyrus only because it resides in Stockholm. It's, of course, of Egyptian origin. And it's a description for how to make the dye indigo. You put in some woad. There are some ancient units in here. Then you pour urine in until the liquid rises over the woad, and you let it be warmed by the sun. And the following day, you get the woad ready in a way that you can tread around it in the sun for 3 days. Some of the prescriptions say that the urine for the best dye should come from men who have drunk strong drink. Okay? So urine is here used as a chemical. Urine is an extremely useful chemical. Initially acidic, it turns basic after a few days. If you go to Pompeii, outside the dyer shops, you will see gigantic urns. Those urns are used to collect the chemicals for the next day's production. And dyeing places, whether in ancient times here, or you can go in Fez in Morocco and see the dyer's market, they never smell very well. And this is part of the story. Here is an article from Accounts of Chemical Research by Patrick McGovern on this industry. What is needed to make a good dye, what one is dyeing in ancient times, is wool first, linen second, and cotton is just coming online about 2,000 years ago. So what one is doing is taking the indigo over here, and it does not bind well to the protein of wool or to the cellulose of linen. And so what one is doing is a simple chemical step, which, since you are chemists, if I were giving to this general audience, I would talk around it, and I would not use the word reduction and oxidation. But what one has to do is a simple reduction to add 2 hydrogens in the classic sense to the indigo, and then in that form it binds better to the protein or the cellulosic material. And then when you take it out of that solution, the oxygen of the air does the oxidation. That's enough. And so that is the basic step that you have to do. In the reduced form, it binds better. This is the only place you'll see me in this lecture. That's my hand there. What we are doing here is we are standing in an ancient Phoenician dye pit at Tel Dor, where the Carmel Mountains turn into the sea, and we are recreating the process. Please don't worry, this is done with modern chemicals, and the yellow actually comes from when you cut out the glands. We had 100 glands. We cut out, it makes a mess. Glands themselves are not too good. But here is the cotton dipped in, and the cotton, it's been reduced. The indigo goes into the cotton, and then we lift it out, and before your eyes, this is not a good slide, but you can see the blue at the top of it. It changes into a blue. Even for a person who's not religious, this is a deeply spiritual moment. I want you to reflect on this, or on what the alchemists did. Taking gold, precious, taking indigo here, precious. Precious because it's gold, precious because it's blue, a dye. That's rare. Putting it into something foul and corrosive, acid, urine solution. Hoping against hope that it'll come back. You have to have faith. If not religious faith, at least the faith of a craftsman or a chemist. And that moment, when you see the blue swimming out, it's wonderful. You see that, and it's something which every human being can share by doing a chemical transformation in a laboratory. I don't have time to tell you the story of the Maya blue. Very interesting indigo product where the indigo is absorbed in polygorskite clay. I saw in some of the posters upstairs a uses of clay for desalination, 2 very nice pieces of work. Here is clay being used to preserve the indigo pigment by intercalation of the indigo into the clay, a remarkable discovery by the Mayans. I want to tell just 2 more stories. The first one has to do with lead. So, the Romans, you are well placed here, we are well placed here to see, because, why are we well placed? We are placed because we are in the heart of the Roman Empire. And they did put under their rule, the entire region of the Mediterranean at one point. But one of the things about Romans, putting aside their military prowess to the side, is they invented modern plumbing. They had a great desire to take baths wherever they went. I have seen Roman baths constructed at Volubilis in Morocco. I have seen them in barbarian England. At lower left, you see a Roman construction from the city of Bath in the UK. They built aqueducts. They led the water in these baths through lead pipes. And the lead pipes were sealed to each other through a lead oxide, minium or litharge, at the joints. Here are some lead bricks marked imperially. They started out making the lead for baths, but then they discovered that normal lead ores contain galena, contain, at least where they got them, for instance, there were large lead galena deposits on the island of Sardinia. They got, the lead deposits contained silver, about 1 part in 600. And the ancient Greek silver mines at Larion were being exhausted, so the Romans started producing silver from lead in vast amounts. Not a very good business, but very easy chemistry. All of us have seen what galena looks like, those beautiful cubic crystals, gross appearance cubic. Galena is lead sulfide. It is easily smelted at not too high temperatures, nothing like the temperatures that the Chinese needed to make the blue pigment or to make porcelain. At relatively low temperatures, lead sulfide is roasted first to a sulfate, and then SO2 is emitted. This is not a very healthy process from beginning to end. The lead oxide is then reduced with charcoal, which is naturally there for the heating to lead. This process is tremendously, it was put together by the Romans on like anything else that the Romans did. They organized this on a vast scale, and I want to give you some interesting scientific evidence for that from a source you don't expect. Oh, you can see a good description of this in Primo Levi's, in one of his Juvenalia chapters, the ones that are in italics in the periodic table, which is one of the 2 great books we have by non-chemists written to, well, he was a chemist. You see him as a chemist that left, a rare picture. It's posed, but he did work in the chemical industry. In there's a beautiful chapter about the mining of the lead and the production of the lead. Let's see. This evidence for the lead mining comes very interesting from a totally different place. This is a European project in Antarctica, but there is one like this in the melting ice cap of Greenland in the northern hemisphere, where people are drilling cores. You can read the cores. An expert the way an expert reads tree rings. You can date the cores because there are different deposits, different rates of snowfall, different thickness in the cores. People can read these. My daughter Ingrid who is a physicist, spent 2 6-week periods on the ice cap of Greenland doing this, which is where I learned part of the story. You can do the analysis, and here is an analysis from a paper in Science of about 20 years ago, where they look at the lead. I want you to see how good the analytical chemistry here is. This is picograms per gram. You do the analytical chemistry on the lead, and now you're going back in time, and you see this peak around 2,000 years ago. And this has been then analyzed in some more detail. This is the raw data that you see from this analytical chemistry of the lead cores. And this is now translated in terms of the world of the lead production, assuming that all the lead that they're seeing in Greenland is coming from Roman sources. This may not be a good assumption because there's some possibly from Chinese sources. But here is this peak of the Roman lead industry, the amount of lead produced by the Romans. So what's happening? Lead is pretty volatile. It's going up both in particulates and as lead itself, and is being blown over to Greenland, just like Japan is worrying about the pollution due to Chinese industry today. This is no different. This is Roman industry, and Greenland not worrying, but should have been worrying about the lead production. That lead production is not equal to about 1800, again, when the Industrial Revolution enters. And then once again, we have lead in the lead cores. No craftsman named here. This is the next to last story. This is from the work of Patrick McGovern. I wish I could. Patrick McGovern is a wonderful person at the University Museum in Pennsylvania, of the University of Pennsylvania. He's a molecular archaeologist, which is a very nice title. And here he's participating in a study of to date, the oldest instance of human beings making intoxicating beverages. Okay? It's China, of course, where old things come from, in Henan province. And there is a burial there. There are ceramic pots in a burial. The ceramic pots are pretty well preserved. The most are in pieces. They analyze some of it, and they find organic residues. The analysis is by GCMS, no different from what you do. You find most decomposes, but you find traces. And the traces are, for instance, of tartaric acid from grapes, from fermenting grapes. Just as you find deposits of tartaric acid in some white wine bottles. But there also are certain deposits from honey. It's very interesting. From honey, what you find the deposits are the waxes. Not the molecules of the honey, but the wax from the combs that goes along. And those are long-chain hydrocarbons. And here is an analysis, for instance, and you don't have to be a chemist to see that these are long-chain hydrocarbons that are coming out in the mass spectrum. So the only thing simple in this world is what happens in your laboratories. Anything that happens in nature is inherently more complicated. The aroma of a good Cabernet Sauvignon has 900 molecules in it. And there's a reason for it, which has to do with the workings of evolution. The first intoxicating beverages, a mere 8,000 years old, here is nothing simple. It's a mixture of a wine, a beer, and a mead. A mead is fermented honey, the wine is fermented grapes, and the beer is, they can identify from the pollen that it's a species of apple that's being fermented, a hawthorn apple. It's quite incredible, but this is rather amusing. So, of course, a modern brewer in the United States, sensing a chance to make money out of this, recreates the ancient Chinese brew. This is Chateau Jiahu. Jiahu is where the finding was made, and here is the propaganda for Chateau Jiahu, which you can read. You could call this extreme beverage a Neolithic grog. It's comprised of honey mead and a combined beer, in quotation marks, or wine, made from rice, grapes, and hawthorn fruit. This is actually Dogfish Head, who is probably the best American brewer of beer and of the new generation. And it's this one tastes okay, but its resemblance to what the original was is probably an accident. The last story I want to tell you is a brief one. It has to do with soap making. So here is a fat, a triglyceride at left. And you make soap by reacting fat with some base, lye, or potash, and you make a soap and you free up glycerin. Some of the simplest chemistry that we have. Now, what was used is, things are complicated. What's used often is a mixture in the ancient production of sodium hydroxide and potassium hydroxide, of lye, strictly speaking in English, lye is sodium hydroxide, potash is potassium hydroxide. Potash is what Davy electrolyzed in order to make potassium for the first time. The potassium hydroxide is, how do you get it? So its name is potash. That's not an accident, that's potash. So what you do is you collect ashes. On a farm, there was no shortage of ashes in the old days from burning. You collect them up and you heat them up in a water solution, you boil them down, and you get a pretty concentrated solution of an alkali, mostly potassium hydroxide. In the old prescriptions I've seen, there's no litmus paper for how to decide how basic you have the potash, no indicator how strong you have it. So there are very interesting prescriptions. One of the prescriptions is you boil the potash and concentrate it down until when you drop a chicken feather in it, the chicken feather dissolves. At this point, it says don't stir it with your finger either. The lye they could get was pretty concentrated. I was very happy when I found this. This is first some photographs from 1911. And here is on a farm in the United States, a rural farm. Here is the wooden structure, and this is a runoff here. This is a primitive chemical apparatus. The ashes are put in there, it's heated, and this concentrated solution, then this first solution, which is moderately concentrated, is then heated in a kettle over here to boil off and to make a more concentrated. The fat, where is the fat? The fat, well, you'll see, there's a quote, which is, I cannot do the accent, but I'll read it. I stopped at a farmhouse to talk with a sunbonneted white woman who was making soft soap in a yard. She had a fire with a great black kettle over it and said she was bilin' the lye. It's just the accent for boiling. It has to bile slow all the morning, she continued, till it's very strong. Then I put in the fat I've saved. Trimmings of meat such as we don't eat, pork rinds, and the cracklings that we have left when we are trying out lard. After the fat is in, I have to stir it every little while with a paddle and be careful not to have it too big a fire or it will bile over. So it simmers along and it's done. When it stood to cool overnight, I dip it out into a flour barrel. If the soap is all right, it's thick like jelly. It's a liquid soap she's making. And I'd much rather have it than the soap you buy. What I make in this kettle will run me a year. When I saw this, I was moved enough to almost cry, because this is what, in a sense, what in this quotation is the whole story of what I want to tell you. This is not chemists, right? These are ordinary people, but they're doing chemistry. This was done on every farm around the world, roughly, until 100 years ago. You didn't buy soap in a store. Yes, maybe you did if you wanted the soap fine and spiced, but for your everyday laundry you made the soap. And you made it by some simple chemistry. So now I come to the end of the story. So I think the stories tell themselves. I don't have to tell you why I'm telling you these stories. These protochemistries. But let me say why, if I reflect on it. First of all, and I'm a theoretician, I think these stories stress the essential importance of experiment and why you cannot substitute a simulation for an experiment. These are experiments with macroscopic substances. And they tell you something about the underlying economics that governs much human activity. You know, that indigo from the snail source cost 10,000 times, roughly the estimate is, the indigo produced from plants. There's a prescription in the Bible for getting the indigo to dye the high priest's robes from snails and not from plants. You can be sure that people are people, and people were people 3,000 years ago, which means that they tried to forge it and to substitute the plant indigo for the snail indigo. And the Talmud has a long discussion of what is essentially analytical chemistry, trying to distinguish the plant indigo from the snail indigo in order to catch the people who made the substitution. People have forged things for a price differential of 1.5. Orange juice has been forged, if you can imagine, by mixing yellow dye and citric acid and water. And so people are people, and chemists are chemists, which means that they can detect forgeries. And how you detect that forgery is an interesting story, whether it is of indigo. If I had time, I would tell you the forgeries of natural vanilla that are made, that are discovered by the French Wine Institute. I look for these stories. Economics governs human activity. These things were made because they were sold. Every one of these items. And they were, interestingly, they were also, this was before patents. So these were propagated in families of craftsmen. These were industrial secrets rather than patents. And they're interesting how that works out. Okay, economics is important. I think that recovering the story of these ancient chemistries renders homage to the past, to the ingenuity of human beings, as if we were the only clever ones in this world. This is why we owe a debt to the people I've mentioned, like Heather Lechtman or Patrick McGovern, who have done the detective work to uncover the unnamed ancestors. Whose ancestors? Our ancestors, the chemists, the craftsmen, craftswomen, who were the chemists. I think these stories connect our world. I feel connected to the woman on that farm who did that chemistry. They connect this world, they normalize science, and they put chemistry squarely in world culture, and not just high culture. There is a world of difference from the Egyptian blue that's used in the gate of Ishtar to the woman doing the boiling on the farm, but it's all chemistry. And it's a story that is worth telling, and that's why I've told it to you. Thank you.